Hi, my name is Paul, and today I want to do a more complex projectile motion. Now, I've already done a projectile motion type of sample problem, but it was a fairly straightforward problem. And in this case, I want to do something a little bit more complex, so it hopefully gives you a deeper insight of how to solve projectile motion problems. So in this case, I have an astronaut named Mark Whitney, and Mark Whitney is sitting on Mars, and he's going to throw a stone off a cliff. And he throws the stone at a particular velocity, at a particular angle, and we're asked a number of things. First of all, number one is how high does the stone get? Number two, how far does the stone go from the edge of the cliff? And finally, what is the velocity at which the stone strikes the ground? So the situation looks a bit like this, and we have here my cliff, and I have here my launch angle, and we're told that the launch velocity is 20 meters per second at an angle of 30 degrees, and we know that the cliff height has a height of 50 meters. And if I were to draw the path like so, it would do like this. And we're interested in what is the height at that particular point, what is the range, what we call our displacement in the x direction, like so, and finally, what is the velocity at which it strikes the ground. So let's set this out. Now, I always encourage my students to set this out in terms of the data, and this will drive our discussion as we go along. So if you look at the vertical aspect and look at the horizontal aspect, because of its projectile motion, the two can be treated independently. And I always say V, U, A, S, T, and I have V, S and T, but of course this S is the Y direction, this S is the X direction. This V and this U over here are both in the Y directions, they're the vertical ones, and this of course is in the horizontal direction. The times here are exactly the same. Obviously the time it takes for the stone that Mark Whitney throws up and down is going to be exactly the same time as the time it moves across. And that's the key to solve projectile motion problems. So now let's put in our data. Remember, the first thing we're interested in is what is the height here. So that's basically what we're interested in. We're interested in this particular height. At least this S that we're going to work out is the height that is just from the edge of the cliff. Now our acceleration here is on Mars, and on Mars the value is negative 3.7 meters per second squared. Our initial velocity is only the vertical component, and that's going to be equal to 20 multiplied by the sine of 30. So we have 20 sine 30, which is equal to 10. Now I'll just leave off the units. Strictly speaking, it has units there as well. Our final velocity is our vertical height, which is going to be 0. It's going to be stationary in the vertical sense. And of course, we don't know the S, that's what we're looking for. So I'm going to put that in there. And in this case, I don't know the time it takes to go up. And in fact, I'm not required to know it in this part of the question. So now I look and say, I've got V, I've got U, I've got A, I need S. So what formulas do I need to use to work that out? Now the formula you should know in this case is going to be equal to V squared is equal to U squared plus 2AS. So notice what I've done. I've drawn the diagram, I've read the question, I've understood the question, R, U, D, the data's down, the diagram's there, and finally I've written the equation E. This is what I call my rude method because I'm actually going through a process of setting this out nicely, and I encourage you to do that. Now you'll see now I've got 0 is equal to 10 squared plus 2 multiplied by my negative 3.7 multiplied by my S, which is what I'm wanting to do there. Now, by the way, before I move on, I've made this negative, so I've actually stipulated, and this becomes very important shortly, is that anything that's going down is actually in the negative direction. This negative is about direction. So you don't have to do that, but you just have to remain consistent in your direction. So I'm going to label this as my positive direction like so. Now, of course, I can work out my answer. I'm not going to do all the rearranging. You can work out S if you like yourself. You're going to get a value of 13.5 meters. Now remember, this is from that height. To show the actual answer that we're interested in is not 13.5, but the value, and I'm just going to say here my answer is equal to 50 plus that, which is equal to 63.5 meters. So there's the answer to the first part. Now for the second part and the third part, I'm going to get rid of this to give us a bit more space to work out the range and the displacement. So let's go. So now that we've cleared our desk, let's write down again the data that we need to work out. So remember V, U, A, S, T and V, S, and t. Remember, this is x and this is y, as in same here and over here. Now, I've done this separately is because now when we're dealing with the second part of the question, then the value that we worked out here before is actually a different situation. We're not just dealing with the situation going up, we're going to deal with the whole situation. So let's write our data down. Now, my initial velocity was still the 20 sine 30, so I'm just going to write that as 10. My acceleration is still negative 3.7. Again, I'm just leaving off the units just for sake of clarity here, but of course they're supposed to be units and I encourage you to do that. In this case, my displacement for the whole journey in the vertical to solve for the range and for my final velocity eventually is the total displacement. Now my total displacement from there to there is actually the 50 meters in the downward direction. So I'm going to put negative 50, right? Because I'm now dealing with the second half of the question. I don't know the time. In the case of the horizontal component, the horizontal velocity is a constant value because it doesn't change because it's projectile motion. So that's going to be equal to our 20 multiplied by the cosine of 30. And that's going to give me a value of 10 root 3. Again, leaving off the units for the moment. My displacement is what I'm looking for, and my time I don't know, but I do need to know the time. And of course, my final velocity I don't know, and I don't need at this state of the problem. So now how do I solve this? Well, there's going to be two ways that you're going to solve this. One's quick, one's a bit longer, but considering the second half is requiring the velocity, you'll see the reason why I go the longer method. But let's deal with the quicker method first. The quicker method says, well, if I write out an equation to work out the range, I need to know the time. The time it takes to go up and down is the time to go across. How do I work out the time? Well, I've got u, a, s, and t, and so I have s is equal to ut plus a half at squared. Now, if I substitute everything in, I get negative 50 is equal to 10, notice it's positive because it's going up, multiplied by t, plus a half of a, which is a half, multiplied by my negative 3.7, multiplied by my t squared. Now, can you see what we are generating here? We are generating an equation that is actually a quadratic formula. If I clean that up, half of 3.7 is 1.85. So I get negative 1.85 t squared plus 10t plus the 50 is equal to 0. Now you see now I have a quadratic that has two factors. Now you have to solve this either through graphical means, you can dump it into decimals and you can get the answer, or you can use the quadratic formula to solve this. Now I'm not going to do the mathematics for you, but the values you're going to get if you do it this short way, you're going to get a value of 8.56 or you're going to get negative 3.16. Now clearly time cannot be a negative. So you can't go backwards in time. So our answer for our time is 8.56. And then, of course, you can solve the actual range by substituting the 8.56 into here, which I'm going to do again in a moment in the longer method. So that's one way of solving for time, and the time you then substitute into this section here. But what I'm going to do now is actually do the long method. How would you do the long method? Well, remember, I'm wanting to know time, but I'm also wanting to know velocity, and I don't know that. So the first thing I can do is I can use two equations of motion and then use the answer for the first one into the second one. What am I talking about? Well, if I use v squared is equal to u squared plus 2as, then I have v to work out, right? That's what I'm wanting to look at. And I get u, a, and s that are given to me. And of course, I can substitute those values in to work out my v. Now, I'm not going to do, again, the calculations, but my v, my final velocity, and this is the final velocity of it landing in the vertical direction only, ends up being 21.68 meters per second. Now, why is that helpful for working out the actual time? Remember, for this aspect over here. Well, now that I've got v, I can use another equation of motion, and that says v is equal to u plus at. But remember, my v is what I've just calculated out. I can then substitute that in. Remember, my initial velocity was my 10 meters per second in the upward direction. My acceleration is my negative 3.7, and now I can work out t. And when you do that calculation, you're going to get that 8.56 seconds. So now that we have our 8.56 seconds, but now also we have the final velocity in the vertical, that sets us up also for the latter part of the question. So how do we first work out the range? Well, the range, of course, which is Sx, is simply the velocity multiplied by the time. My velocity in the horizontal direction hasn't changed. It's still 10 root 3. And then we simply multiply that by my 8.56 seconds, and I'm going to get a value of 148.3 meters. So Mark Whitney's stone travels 148.3 meters away from the edge of the cliff. Now, the last part of the question. We need to work out the velocity, but it's important to understand that the velocity of the stone hitting the ground is a combination of both the horizontal velocity and the vertical velocity. Now the horizontal, in other words, the angle at which this lands here like so, is a combination of what happens horizontally and what happens vertically. Now, remember I said, already know the horizontal velocity because it doesn't change, it's constant. But I've also now already worked out the velocity in terms of the vertical velocity. So I can now put those two together to work out the final velocity. Now, how do I do that? Well, I start off by drawing a lovely vector diagram. So this is my velocity of the stone in the horizontal. Remember, that is equal to 10 root 3. It is also traveling vertically. I've already worked that out. That's 21.68. And then, of course, this is the velocity I'm interested in. And that has two components. It has a component that is its magnitude, which is the v we're after, and also its direction. Remember, v is a vector, so you need to provide the direction as well. So how do I work out v? Well, that's pretty clear. We know that v squared, using Pythagoras, is 10 root 3 all squared plus my 21.68 all squared. Now, that means if you do the calculations, you're going to get a value of 27.75 meters per second, right? But I haven't finished yet. Remember, I need to know the direction. Well, again, this is where trigonometry comes really handful. You see that the tan of the angle is equal to the opposite, which is 21.68, divided by my adjacent, which is 10 root 3. If you work out the angle, that angle ends up being 51.4 degrees. So as a quick reminder, if you set everything out, draw a diagram, write down the data, substitute in the data that you're given, and then write down the equations because you can see which variables you have and which you don't, you're going to find that any projectile motion problem you do becomes much, much simpler to solve because all you're dealing here is with algebra. I hope that has helped you understand projectile motion. My name is Paul from Physics High. Please like, share and subscribe. Put a comment down below if this has been helpful for you. Take care and bye for now.